Hello students, good morning everybody. In today's video, we are going to see about capacitors. What is a capacitor? A capacitor is a device used to store electric charge and electric energy. A capacitor consists of two conducting plates. The plates may be either made of plain sheets or plates, and two plates are separated by a small distance in a capacitor. Capacitors are widely used in many electronic circuits and also used in applications in our daily life. A simple capacitor consists of two parallel metal plates separated by a small distance. It is shown in the figure. These are the two plates of the capacitor. The two plates are connected or kept parallel to each other. See, in the second diagram, you can able to see the capacitor plates are connected to a battery. A battery is a source of DC voltage. It is a source of potential difference. When a capacitor is connected to a battery of potential difference V, what happens? The electrons are transferred from one plate to another plate by the battery, so that one of the plates becomes negatively charged. That is, this plate becomes negatively charged and the other plate becomes positively charged. So what happens because of the transfer of charges, a potential difference equivalent to the potential between the two terminal voltages of the battery will be produced across the two plates of the capacitor. If you increase the battery's voltage, then what will happen? The amount of charges stored in the plates also increases. So in general, I can say the charge stored in a capacitor is proportional to the potential difference between the two plates. That is, if you increase the terminal voltage of the battery, the charge to the plates also increases, and if you decrease the terminal voltage, the charge also decreases. So I can write here Q is directly proportional to V. That is, if V is increased, Q also increases. If V is decreased, Q also decreases. So I can write Q is proportional to V, or Q is equal to CV. What does the C represents? The C is a constant of proportionality or proportionality constant, and this is called as capacitance of the capacitor. It is always represented by the capital letter C. So how will you define capacitance of a capacitor? Capacitance of a capacitor is defined as the ratio of the magnitude of charge on either of the conductor plates to the potential difference existing between them. So I can write C is equal to Q by V. You can able to see here C is equal to Q by V, where C represents the capacitance of the capacitor. The SI unit of capacitance is coulomb per volt or farad. This farad is named after the honor of Michael Faraday. Farad is a larger unit of capacitance, but in practice, capacitors are available only in the range of microfarad or picofarad. 1 microfarad is nothing but 1 μF is equal to 10 power minus 6 farad, and 1 picofarad, 1 PF is equal to 10 power minus 12 farad. A capacitor is always represented by the symbol like this. You can note here that the total charge stored in the capacitor is 0. Q minus Q is equal to 0. We are saying that the capacitor stores charges. It means the amount of charge that can be stored in any one of the plates. This diagram, this photograph shows you various number of capacitors which are available in various shapes for our practical life. Some are cylindrical in shape, some are disc-like shape. And capacitors can also of different types like tantalum, ceramic and electrolytic capacitors. These capacitors are now extensively used in various kinds of electronic circuits. The next one is we are going to derive an expression for capacitance of a parallel plate capacitors. That is, we are going to derive an expression for capacitance C of a parallel plate capacitor. What do you mean by a parallel plate capacitor? A parallel plate capacitor consists of two parallel plates, each of cross-sectional area A, and these two plates are separated by a small distance d. Okay, the electric field between the two infinitely parallel sheets is uniform, and it is given by E is equal to sigma by epsilon naught. You have come across this expression in one of the applications of Gauss law. So using one of the applications of Gauss law only, we are writing the electric field between the two parallel plates, which is E is equal to sigma by epsilon naught. What does this sigma represents? Sigma represents the charge per unit area of the capacitor plates. That is, it is called surface charge density. If the separation d between the plates is very smaller than the size of the plates, that is, if d square is very smaller than a, then the above result can be used even for a finite sized parallel plate capacitor. This diagram shows the parallel plate capacitor. This is one plate and this is another plate. This plate is having a positive charge plus Q. This plate is having a negative charge minus Q. Between these two plates, there is a uniform electric field existing between the two plates. The two plates are having an area A and the two plates are separated by a small distance d. Now the electric field between the two plates is E is equal to Q sigma by epsilon naught. Instead of sigma, you substitute Q by A. So E is equal to Q by A epsilon naught. Since the electric field is uniform between the two plates, the electric potential difference between the two plates is given by V is equal to E into D. So you take this E value and substitute it here. You will get V is equal to QD by epsilon naught. Therefore, the capacitance of the capacitor C is equal to Q by V, which is equal to Q by QD by A epsilon naught. Q get cancelled, so the above result becomes A epsilon naught by D. So this equation indicates that the capacitance is directly proportional to the area of cross section and inversely proportional to the distance between the two plates. So from the expression, it is clear that if the area of cross section of the plates is increased, more charges can be distributed to the for the same potential difference. As a result, what happens? The capacitance increases. The next one, if the distance d between the two plates is reduced, what will happen to the potential difference? You know that the potential difference V is equal to ED. So when d decreases, V also decreases. And as V comes in the denominator in C is equal to Q by V, when V decreases but E remains constant. As a result, voltage difference between the terminals of the plate battery increases, which in turn leads to the additional flow of charge to the plates from the battery till the voltage on the capacitor equals to the battery's terminal voltage. Suppose the distance is increased, the capacitor voltage also increases and becomes greater than the battery voltage. Then the charge flow from the capacitor plates to the battery till both the voltages become equal. Now we are going to see the expression for energy stored in the capacitor. A capacitor not only stores the charge but also stores energy. When the battery is connected to the capacitor, what will happen? Electrons of total charge minus Q are transferred from one plate to another plate. So to transfer the charge, work is done by the battery. The work done by the battery is stored as electrostatic potential energy in the capacitor. So if you want to transfer a very small charge dq to a potential difference V, the work done is given by dW is equal to V into dq. So what is V? V is equal to Q by C. Therefore, the total work done to store the charge in a capacitor is W is equal to W is equal to integration from 0 to Q, QC by D, Q by C into dQ. So when you differentiate this, you will get the expression for work done as Q square by 2C. This work done is stored as electrostatic potential energy UE in the capacitor. So what is the expression for electrostatic potential energy of a capacitor? The expression for electrostatic potential energy of a capacitor UE is equal to Q square by 2C. And you know Q is equal to CV. So instead of Q, if you substitute C square V square in this expression, the above expression will also become half CV square. So there are two expressions for electrostatic potential energy of a capacitor. The first expression is Q square by 2C, and the next expression is half CV square. So whenever you are doing problems, you can use either this formula or this formula. The energy stored in this is directly proportional to the capacitance of the capacitor and the square of the voltage between the plates of the capacitor. The next one is, this is a very important question. The next one is, where is the energy stored in the capacitor? To understand where the energy stored in the capacitor, the above equation can be rewritten as follows using like this. That is, instead of C, you use the expression A epsilon naught by D. Already we have studied. And instead of V, you substitute the equation ED. You substitute these two values in the above expression 1.87. You will get UE is equal to half into A epsilon naught by D into E D square. So after that, the above expression will turn out to be half epsilon naught into AD into E square. What is AD? AD represents the volume of space between the capacitor plates. Therefore, the energy stored per unit volume of space is defined as energy density, small UE, which is equal to U by volume. So UE is equal to half epsilon naught E square. From this, it is clear that the energy is stored in the electric field existing between the two plates of the capacitor. Once the capacitor is allowed to discharge, the energy is retrieved. It is important to note that the energy density depends only on the electric field and not on the size of the plates of the capacitor. This equation is valid. 1.89 is valid, but for the electric field due to any type of charge configuration. Next, we will see about the applications of capacitors. These capacitors are playing a very important role in our ordinary daily life. Let us see a few of the applications. Flash capacitors are used in digital cameras for taking photographs. The flash which comes from the camera when we take a photograph is due to the energy released from the capacitor, which is called as a flash capacitor. It is shown in the diagram in this photograph. The next one is during cardiac arrest, a device called heart defibrillator is used to give a sudden surge of large amount of electrical energy to the patient's chest to retrieve the normal heart function. The next one, capacitors are used in the ignition system of automobile engines to eliminate sparking. Capacitors are used to reduce power fluctuations in power supplies, and they are also used to increase the efficiency of power transmission. Capacitors have large number of disadvantages also. Even after the battery or power supply is removed, the capacitor stores charges and energy for some time. For example, if you take the TV, suppose if the TV is switched off, it is not advisable to touch the back side of the TV panel, because from the capacitor of the TV some light will flash, some energy will be coming out. So you are not advised to touch the back side of the TV panel if the TV once the TV is switched off. So these are some of the disadvantages of a capacitor. Now let us see the effect of dielectric in a capacitor. In the previous discussion, we have seen that the capacitance of the capacitor is given by the formula C is equal to A epsilon naught by D. And here the plates, with the space between the plates is filled with air. Suppose if if you fill the space between the two plates with the material like dielectrics like mica, glass and paper, let us see what will be the capacitance of what will happen to the capacitance of the capacitor. So if you insert a dielectric between the two plates of a capacitor, the capacitance can be adjusted in two different ways. The two ways are when the capacitor is disconnected from the battery, let us see what will happen to the capacitor, and when a capacitor is connected to the battery, let us see what are the effects, what are the changes in the capacitor. The first case, when the capacitor is disconnected from the battery. Consider a capacitor with two parallel plates, each of cross-sectional area A, and the two plates are separated by a small distance D. The capacitor is charged by a battery of voltage V0, okay, and the charge stored is Q0. Now what is the expression for the capacitance of the capacitor? The expression is C0 is equal to Q0 by V0. Now the battery is disconnected from the capacitor. You have to note this point clearly. The battery is disconnected from the capacitor, and the dielectric slab, say mica slab or glass slab, is inserted between the two plates. This is shown in the diagram. Let us see this one. What happens? In this diagram, the capacitor is connected to the battery. The electric field lines will pass through this. The battery is removed and inserted dielectric. See, the green colored portion gives you the dielectric. The dielectric has a relative permittivity epsilon r. The introduction of dielectric between the plates will, what will it do? It will decrease the electric field. You have to note it in different stages. The first stage is when you remove the battery and when you introduce a capacitor. Dielectric, the electric field between the plates is decreased. It is experimentally found that the modification on the electric field is E is equal to E0 by epsilon r. E0 represents the electric field inside the capacitor, and when there is no dielectric. But if you introduce a dielectric, if epsilon r is the relative permittivity of the dielectric, or which is simply known as dielectric constant, for any dielectric, since epsilon r is greater than 1, the expression for the electric field between the two plates with the capacitor dielectric is E. So when epsilon r is greater than 1, as it is in the denominator, E decreases. So I can say E is less than E0. As a result of the decrease in the electric field, the potential difference between the two plates V is equal to ED also decreases. But at the same time, in this case, the charge Q0 will remain constant once the battery is disconnected. So here what is happening after the battery is removed and the dielectric is introduced? Here the electric field decreases. As a result, the potential decreases, but the charge remains constant. So as it is happening here, V is equal to ED, which is equal to E0 by epsilon r into D, which is equal to EV0 by epsilon r. So now the capacitance C is equal to Q0 by V, which is equal to epsilon r into Q0 by V0, which is equal to epsilon r into C0. You know that epsilon r is greater than 1. Since we have epsilon r is greater than 1 and we have C is equal to epsilon naught into C0, we have C is greater than C0. Thus it is clear that on insertion of the dielectric, the capacitance increases. Using equation, previous equation, you know that C is equal to A epsilon naught by D, but here where the dielectric is introduced, the expression becomes A epsilon naught epsilon r by D, and here A epsilon naught by D is nothing but sorry, epsilon naught epsilon r is nothing but epsilon, so C is equal to A epsilon naught by D. So it is clear that when a dielectric is introduced with the battery removed, the first point is electric field decreases, the potential also decreases, but the charge remains constant. So when the potential decreases, the capacitance increases. Now in this case, let us see how will the energy stored varies. The energy stored in the capacitor before the insertion of the dielectric is given by UE is equal to half Q naught square by C naught. Okay, after the dielectric is inserted, you all know that the charge Q naught remains constant, but the capacitance is increased. As a result, the energy stored decreases because this term increases and this term constant. So what will happen to the energy store? It stores decreases. So U is equal to half Q naught square by C, which is equal to half Q naught square by 2 epsilon naught, sorry, half Q naught square by epsilon R into C naught, which is equal to U naught by epsilon R. Since epsilon R is greater than 1, we have U is less than UE. U naught. There is a decrease in the energy because when the dielectric is inserted, the capacitor spends some amount of energy in pulling the dielectric inside. So it is clear that when a dielectric slab is introduced between the plates of a capacitor and when the battery is removed, the electric field decreases, the potential decreases, the charge remains constant. So capacitance increases but the energy decreases. This is very important. Let us now see the case what happens to the capacitance when the battery remains connected to the capacitor. Let us now consider what happens when the battery of voltage V0 remains connected to the capacitor when a dielectric is inserted into the capacitor. In this diagram, we can able to see this is a capacitor, a battery is connected and we are not disconnecting the battery is connected as such. Now we are introducing a capacitor. It is found that with the battery connected between the plates and if a dielectric of dielectric constant epsilon r is introduced between the plates, it is found that the potential remains constant but the charge increases. Okay, so how will the charge increase? The charge is given now. The present charge after the battery dielectric is introduced is Q is equal to epsilon R into Q naught. Q naught is the original charge when no dielectric is, the initial charge when no dielectric is introduced, but after the dielectric is introduced, the value becomes like this. As epsilon R is greater than 1, Q increases. Due to the increased charge, the capacitance also increases. So what is the new capacitance? The new capacitance is C is equal to Q by V naught. It should be noted that V naught remains constant. Q increases, is it not? As Q is in the Q is in the numerator, and V naught remains the same. As Q increases, C also increases. That is C is equal to epsilon naught Q naught by V naught. Q naught by V naught is nothing but C naught. So C is equal to epsilon R into C naught. However, the reason for the increase in capacitance in this case when the battery remains connected is different from the case when the battery is disconnected before introducing the capacitor. Now C naught is equal to A epsilon naught by D and C is equal to epsilon naught A by D. The energy stored in the capacitor before the insertion of dielectric is UE is equal to half C naught V naught square. Note that there we have not used the expression U naught is equal to half Q naught square by C naught because here both the charge and the capacitance are changed whereas the V naught remains constant. After the dielectric is inserted, the capacitance is increased, here the total energy is also increased. But in the previous case, when the dielectric is introduced, the energy decreases. But here, when the battery is connected or remains connected, the energy also increases. U is equal to half C V naught square, which is equal to half epsilon R C naught V naught square, which is equal to epsilon R U naught. Since epsilon R is greater than 1 and we have U is greater than U naught. Okay, it must be noted that since voltage between the capacitor V naught is constant, the electric field between the plates also remains constant. The energy density is given by U is equal to half epsilon E naught square, where epsilon naught is the permittivity of the given dielectric medium. The results of the above discussions can be summarized here, and let us discuss C to it. The table shows you the effect of dielectric in capacitors. When the battery is disconnected and the dielectric is inserted, the charge remains constant, potential decreases, electric field decreases, capacitance increases, energy decreases. But when the battery is connected after the insertion of the capacitor, the charge increases, voltage constant, electric field also remains constant, capacitance increases, and the energy decreases. So in both these cases, we have found that even if the battery is connected or disconnected, the capacitance increases in both the cases. But when the battery is disconnected, the energy decreases, and when the battery is connected as usual, the energy increases. Okay girls, thank you.